Welcome back, everyone, for the final session of today's ESA Scout HydroGNSS workshop. The final session is a follow-on on the HydroGNSS mission and some research topics on GNSS reflectometry. The chairs for this session are Dr. Estelle Cardelac, GNSS-R researcher from the IEEC, and Dr. Martin Unwin, Principal GNSS Engineer from SSTL. Estelle, over to you.
Yes, I think Martin will introduce the speakers.
Okay, I shall
take care of the questions.
I shall introduce the speakers. Thank you very much, Ben, Estelle. We have some bad news and good news. So bad news is, unfortunately, Klaus Scipal can't be with us. For personal reasons, he had to drop out. He sent a message last night, so we wish him well. The positive side, the silver lining to that cloud, because it was a very good talk and we were looking forward to it, but the positive side is that means that we can catch up with our schedule. We'll slip our 2 presentations now into the subsequent slots, and then we'll be on time. So without further ado, then I'll hand over to Andy Newton, who is a senior ground segment engineer in SSTL, and he'll be talking about the HydroGNSS ground segment, Pdgs, and user access. Over to you, Andy.
Thanks, Martin. Just share my screen. I'm going to play back a recording that I've made of the presentation. So can you see that now?
Yes.
Good. I'll start it off then.
Can't hear a sound at the moment. Is
sorry. Sorry. Let's start again then. Sorry. I'm not sure how I fix this, to be honest.
Sam, do you have a copy of the video? Or does that somebody know how to get the sound out?
Yeah, I mean, Sam should have a copy of it.
Yeah, I'm just wondering, I'm trying to remember. But
change the audio settings, so the
yes.
computer, the audio of the computer is redirected to the Zoom session, something like this. I don't know exactly how it goes.
Yes, I'm trying to remember where that appears. Okay, so when you share the screen, you have to check this video sound. Okay, so if you stop sharing the screen and then share it again, I think this is the key.
Okay.
So if you stop sharing the screen and then try sharing it again, and look, there's a little box that's share sound.
So how do I stop sharing the screen? So
at the top of the screen, there's a red button. Red. If you go up to the top.
Yeah. Oh yeah.
Stop share. Yeah, go to stop share.
I don't see that.
Do you not see that? Is there a stop share? Is there a stop share at the bottom? It's usually at the top.
I don't see that. Can you just take back the screen? Then I share it again.
It says I can't share while someone's. Okay, hold on.
Leave gets me out of the whole thing.
Oh, Sam's sharing it. Okay, so Sam needs to do this.
Sam, just start it off then.
Is it okay, Sam? If you're ready to play, let's try playing and see whether we can get the sound. I don't think we're getting the sound, so maybe Sam needs to do that. So Sam, if you can stop sharing and then share again, but click the little that says share sound. So you need to actually stop sharing, I think.
Where's the stop sharing button then?
Well, you don't have it.
Right.
That's he's done it.
Yeah.
So then when you share, Sam, click the little, there should be a little checkbox that says share sound.
And I'm going to be talking about the HydroGNSS.
Right, over to Andy.
Hello, I'm Andy Newton, and I'm going to be talking about the HydroGNSS ground segment. I'll be talking about the ground segment context and its relation to the space segment. Ground segment overview and diagram, description of the spacecraft operations center and mission operations center and their components, then some more detail on the main mock components of interest to this workshop, i.e. the Pdgs and the web portal. Then a look at SSTL's MERBIS software used for TDS1, and finally the conclusions on the HydroGNSS ground segment. So this diagram is really a mission overview, but it is useful to set the context of the ground segment. From top left, we have the HydroGNSS satellite unfolding its solar panels after launch. At the top, we have the GNSS satellites. Their GNSS signals are reflected off the ground and are received by the HydroGNSS Nadia antenna, which will of course also receive but it will also, of course, receive direct GNSS signals with its zenith antenna. The direct signals are not shown in the diagram to avoid overcluttering it. S-band TT and C links and X-band payload data download will be through the primary KSAT Svalbard ground station. There will also be backup ground stations at SSTL. SSTL will handle spacecraft platform operations through the Guildford SOC, and mission operations, including mission planning and payload data processing, will also be at SSTL. This will also include dissemination of data products to the user community. The ground segment top-level components are Spacecraft Operations Center, which is the standard SSTL SOC based in Guildford, currently in use for multiple missions. Components are the mission control system software, plus flight dynamics and contact scheduling software. The ground stations are the KSAT Light Svalbard ground station for primary S and X-band operations, backup TT and C through the SSTL BA S-band ground station, also backup S and X-band through a new SSTL ground station here in Guildford, and the Viasat Real-Time Earth ground station. And both these stations are at SSTL HQ in Guildford. The Mission Operations Center is also based at SSTL. It consists of the mission planning system, which plans mission operations and generates payload and ground station schedule files. The payload data ground segment, which is the processing system for the GNSS-Reflectometry payload data, extracting DDMs from it, and then generating L1A, L1B metadata, and the L2 and L3 climate data products. Finally, a web portal which allows users to browse and download the GNSS, the HydroGNSS products. So this slide shows graphically what was described on the previous slide. At the top, we have the ground stations, including the primary KSAT ground station in Svalbard, and the backup SSTL and Viasat ground stations. The payload data downloads from the ground station are shown as broad pale blue arrows, turning purple as the data is processed by the Pdgs and stored on the mission archive, and then red when the products are downloaded by the user community. Other key flows shown are payload skeds from the mission planning system to the mission control system for upload to the satellite ground stations. Spacecraft logs such as GP logs, EWODs and AOCS logs are downlinked to the Pdgs via the ground stations, and input of raw reflectometry requests to the MPS. So the Spacecraft Operations Center. So it contains the SSTL mission control system software with facilities for pass automation by the track program, which runs scripts automatically at acquisition and loss of signal, telecommanding manually or via skeds, real-time telemetry display, file transfers to and from the OBC clock synchronization, and in addition to the mission control system, there is also ground station availability planning software, that's GAPS, for managing pass conflicts between the satellites and ground stations. There's also Javelin orbit management software for TLE generation, maneuver planning, and propellant mass monitoring, and the contact broker for booking the KSAT passes. The SSTL SOC currently manages the missions shown in this table. The missions in red have exceeded mission lifetime and are still operating. The grey ones, for example, the top two, have now completed all their operations. The operations include TT&C activities, calibration, monitoring spacecraft health, platform anomaly detection and resolution, and orbit maintenance. For constellations such as RapidEye and DMC3 and S1/Novasar, the orbits are phased to prevent pass conflicts between different satellites in the constellation. For several missions, SSTL has provided a full ground segment at the customer site, and it's operated by the customer themselves. So here is the SSTL SOC. From here, SSTL can handle all phases of a satellite mission, from the launch and early orbit phase and through commissioning to either hand over to the customer or to start of service for managed missions. From the Guildford SOC, SSTL can operate through all the available ground stations, the SSTL owned, KSAT and the Viasat RTE. All the applications run on a virtual SOC, vSOC central server. Network terminals are used to connect to the relevant mission control system applications and other applications as required in the vSOC. By the way, I'm in the photo wearing a red t-shirt on the right of the photo. So the Mission Operations Center, of which the components are the mission planning system, which plans payload operations and payload data downloads, manages onboard resource usage, and also generates payload and ground station schedules. The payload data ground segment, which processes the payload data files to generate all the L1, L2, and L3 products, which it stores on a NAS data archive. The data is then backed up to an offsite facility, which also has the PDGS software virtual machines, so it can be used for reprocessing of the back catalog if there is an update to the PDGS modules during operations, requiring a large amount of reprocessing. The PDGS server will also host an end-to-end simulator used primarily for pre-launch testing. Initial testing and software development will be with a prototyping server, which we already have and are currently setting up. The web portal allows users to browse products and download them from the SFTP server via a dedicated internet link. It also provides other useful features, such as downloadable Python and MATLAB samples to show users how to access and display the products. So here's a brief overview of the Pdgs and simulator processing flow. The simulator from Sapienza and IEC generates L1A DDMs and L1A metadata, whereas in the Pdgs, these L1A products are generated from L0B DDMs and spacecraft logs. The SSTL L1B processor and additional L1B modules from SSTL, NOC, and IEC generate further L1B metadata. The L1 metadata files are then merged into a single L1 metadata file, and then the L2 processors implemented by the science partners generate the L2 climate variable products. The L2 data are collated and regridded into L3 monthly maps, not shown in the diagram, and MB for the forest above ground biomass. The maps are generated every 6 months rather than monthly. So this table shows a summary of the main PDGS processing modules. The green modules are level 1, L1A, which converts the L0B DDMs into NetCDF format and collates information in spacecraft logs and payload data into L1A metadata. Then the L1B processor incorporates auxiliary data and generates derived metadata, including radiometric calibrations to form L1B metadata. There are also 3 L1B extension modules which generate further L1B metadata. And all this metadata is combined into a single L1 metadata file. Then the blue section shows the 5 modules that generate L2 climate data products, which are surface soil moisture, freeze-thaw state, surface inundation, forest biomass, and ocean wind speed and sea ice extent. So the PDGS will be based on a server SSTL running 2 VMs, 1 Windows and 1 Linux, allowing science partners to have the choice of operating system. Both VMs will use a main data archive with all raw data and PDGS products for the mission. The mission data will also be backed up to offsite storage, which will also include a full backup PDGS processing chain. The products available to the user community will be copied over to an SFTP server. There will also be an associated web server, allowing users to view information about the mission, browse through products, and download code samples to show how to load and display the products in Python and MATLAB. Users can download products from the FTP server, and sample scripts will be provided to show how to do this. So the HydroGNSS web portal will be based on the Merbis website, which is in use for TDS1. The website front page and URL are shown on the picture below left. Merbis itself stands for Measurement of Earth Reflected Radio Navigation Satellite Signals by Satellite. And Merbis also includes the predecessor of the PDGS used for processing TDS1 data. It was developed in partnership with the National Oceanographic Center, and on the bottom right, there's a picture of a monthly map of sea ice extent data. For Merbis, the two L2 products generated by the NOC software are sea ice extent on the left, shown here for the Antarctic, and ocean wind speed on the right. Both of these plots are monthly maps for late 2018. So in conclusion, the HydroGNSS ground segment will be based on platform and payload operation systems already in use on successful SSTL missions. The ground segment is easily scalable to a constellation, as has been proven on several missions. So building on this, the Pdgs will implement some major new features. Use of both GPS and Galileo signal reflections, dual frequency and dual polarization from both of the GNSS constellations, and the use of coherent measurements as well as DDMs. And finally, there will be new climate products of freeze thaw, surface inundation, soil moisture, and forest above ground biomass.
Thank you, Andy.
Yep, that's the end of the presentation. So are there any questions?
There is a comment by John Eyre. He mentions that the regraded products are not L2, they are L3. And also that some applications like numerical weather prediction, L2 products will be more useful. Ungraded in space and unfiltered in time. Yeah, I think this is important information. We are aware that different fields of applications might require different types of data. So I think it's important that we collect all these sort of requirements from different communities.
Yeah, I think that's sort of under discussion right at the moment, isn't it? That some of the partner algorithms are going to deliver gridded data and others aren't. So we need to try and coordinate that and come up with sort of a consistent approach.
Yes, it may be there's scope for both, because I think the reason for gridding is that you get the better results, which we're trying to achieve in this mission. But maybe we can also give access to the track data before it gets to the gridded point. So that it's up for discussion.
So were there any other questions?
No.
No. Okay. Well, in which case, thank you very much, Andy. And we'll go on to the next presentation. And so it's going to be Mauro Pierdicca, who we've heard from already, will be talking about the end-to-end simulation for HydroGNSS. And Gabrielle Marigold is also mentioned as the SSTL coordinator working closely with the end-to-end simulation. But I think the presentation is going to be given by Mauro. So hand over to Mauro. Are you there, Mauro? If you're there, you're muted and your camera's off.
Okay. Now I've been enabled to speak. Hello.
Okay. Yes.
Okay.
Hello.
Finally. Okay. So I will share the screen. Okay. Can you see the screen? Full screen?
Yes, we can.
Okay.
Thank you.
So first of all, I would like to acknowledge my colleague from SSTL, from Tor Vergata University of Rome, from Sapienza, and from IEEC. I'm going to speak about the end-to-end simulator, mainly from the point of view of the scope and the requirements of the system, the functionality and the architecture, the scenario that we will consider for the simulation, the first and second order effect that we are going to simulate at different steps, because the first order will be implemented at PDR and the second order at CDR. And then I will show how we intend to use this simulator to finally assess scientific readiness level 5. Let's say, target interaction models that are embedded into the simulator will be presented tomorrow by Leila Guerriero from Tor Vergata University. So the main scope of the end-to-end simulator is to demonstrate the achievement of a scientific readiness level 5. The simulator that is rooted mainly on previous software developed by Sapienza and Tor Vergata University, based on internal finding, but also based on some project funded by ESA. But it is also taking advantage from some modules that are included in the WebPy software that has been developed by IEC. This is the definition of the end of the scientific readiness level 5 from ESA. So the main functionality of the simulator will be simulating level 1A and level 2 data from HydroGNSS for a number of scenarios on the Earth, which include test cases associated to the different product of the HydroGNSS emission. That is agricultural area or forested area for estimating soil moisture or forest biomass. Other area devoted to the generation of frozen and thawed change product, and other area that will represent a case of the water body or inundation product. For each of these area, we will be able, using the simulator, to change the parameters that characterize each plot of the area itself. So, for instance, we can change the biomass of the cover of the forest cover of the area, or we can change the soil moisture of the bare soils. So the end-to-end simulator shall enable to assess the performance of HydroGNSS, considering the variability of some confounding geophysical parameters, that is the effect of the roughness when targeting the soil moisture, just to give you an example, but also considering the errors that can be introduced by imperfection of the platform or the instrument or any noise source. Then the simulator should also be able to assess the sensitivity of the observables, for instance, the reflectivity, both to change in the geophysical parameters of the target, and also to the effect of some instrumental errors. As I said before, for each case, that is bare soil, agricultural or forested area, free-stow, and the water bodies, we will consider a real scenario, that is a real area with its digital elevation model, its land cover, but we will be able to change the parameter of each type of cover of the scenario and also, of course, the system effect to try to see the effect, to understand the effect on the measurements and also the effect on the final retrieval. As I said before, we will implement first some simulation of the common observables which are already available from satellite, specifically the delayed Doppler maps and the reflectivity, that is a sort of power observable. And then in the second step at the CDR, we will include also second order observable, that is the new capability of HydroGNSS, such as the complex channel at high rate and the dual polarization capability. So this is the architecture of the simulator. This part is what was in the past already developed by Sapienza and Tor Vergata University with the contribution from IEC. And this part is going to produce a level 1A data. And then we have to integrate this module with the level 1B processor, where the calibration will be carried out. And this will be developed by SSTL and NOC. And then the level 1B product generated by the level 1 processor will be injected into the level 2 processor that will produce the 4 different products from HydroGNSS. So what we have to do at the end is through this performance assessment module to compare the input that we have provided to the simulator in terms of geophysical variable with the output at the end of the complete chain to assess the performance of the retrieval with different instrument effect provided during the simulation of the level 1A product. So this is the main scope. So as we said, we are going to consider a number of scenarios, order of 2 scenarios for each application, so a total of 8 different scenarios. We have selected these scenarios based on the chance of getting in the future also in situ data for the final validation of the mission. This is still something we have to refine also with the help of the SAG. For instance, we are considering as full soil moisture the San Luis Valley. There is also considered as a test site for Cygnus, or the southeast of Australia, where there is a very nice network of in situ soil moisture measurements. And as for Fristo, we are considering these 2 sites that are also core sites for this map mission. So then, as I said before, we will start, and we have already implemented the most of this system effect. For instance, the possible change in the GPS and Galileo transmit power that we know it is not very stable. The effect of the noise related to the noise inside the receiver, but also to the external noise producing an equivalent antenna temperature, which depends also on the scene, but can be increased by incoherent man-made type of noise, for instance, a reflection from other satellites. And then we will introduce the effect of the change in attitude or poor determination of the satellite attitude, the effect of the fluctuation due, for instance, to speckle type of noise, the imperfection in the characterization of the receiver, for instance, the non-perfect transfer function of the receiver, and then the effect of the mismatch, the polarization mismatch of the antenna, both the receiving antenna aboard the HydroGNSS and possibly also the mismatch of the transmitting antenna from GPS and Galileo satellite. As a second order, we will include the new observable from HydroGNSS, that is also the right polarization and the coherent channel. This module will be provided by IEEC, and we will improve, when possible, the model to account for system effect, because, for instance, once the HydroGNSS antennas will be very well measured on ground and well characterized also from the point of view of polarization purity, we can implement a better model to account for polarization mismatch. We could also include some a model to account for atmospheric attenuation, although we do not expect significant effect of the troposphere in the scatterometric measurements from HydroGNSS. And we could also include, for instance, a variable antenna temperature due, for instance, to the effect of the reflection from other satellite. So these are examples of the model that are implemented inside the simulator to account for the noise from the antenna and from the receiver, to account from thermal noise, which is a fluctuating type of noise, of course, and also speckle noise. We can introduce a modulation transfer function of the receiver, as well as a covariance matrix, which provide a correlation between different elements of the delay Doppler map in delay and Doppler, as well as a change in the transmitter power or a different pattern of the transmitting antenna, or an error in the pattern of the transmitting antenna. Then, as for the polarization mismatch, at the moment we have implemented a very simple model which assumes a pair of dipoles, so a very simple model of the antenna polarization efficiency. And then, as for the attitude effect, we are considering, of course, the different reference system between satellite body and orbit frame, and then the antenna frame with respect to the body frame, which at the end will provide the possibility to compute the gain of the antenna, both the up-looking and down-looking antenna toward the transmitter and the target respectively. So in this way, we can account for any change of the attitude or poor determination of the attitude of the satellite. How we were going to use this simulator? We will start, as I said before, from a real area with a certain land cover map. We may change the geophysical parameters that characterize each of these areas. For instance, we can change soil moisture, forest biomass. So to give an idea of this, I have put here the same map, but different colors to make it clear that we are changing the geophysical parameter. Then the level 1 processor simulator, sorry, what we call H7 will produce L1A data, adding also some system error, as mentioned before. At this point, this level 1A product will be passed to the level 1 processor that will produce a level 1B, and then the level 2 processor will produce finally the geophysical output. At this point, we have to compare this product here with the input parameter that we have provided to the simulator. So for instance, as for level 1, we can compare the reflectivity which has been simulated by the H7s that theoretically that we'll assume in this case as the true reflectivity, with the reflectivity which has been estimated from the level 1B calibration processor which is not properly accounting, we are assuming is not probably accounting for the system error. And we can create a scatter plot, produce, for instance, a root mean square error between the true reflectivity simulated by H7 and the one produced after calibration. As for level 2, in this case, for instance, we can compare the moisture that or biomass that we have provided to the simulator, to the H7 simulator, with the moisture or biomass that are have been generated at the end of the complete processing chain. And once again, we can compute a correlation coefficient or root mean square error to measure the performance of the retrieval. This is in case of the moisture or biomass, which is a continuous variable. In case of a freeze-thaw and or inundation, this is not a continuous variable. This is just a flag. And so we can build a confusion matrix to provide, which is the final accuracy of the level 2 processor. So basically, in terms of the use of the simulator, we will have, we already have an interface providing most of the input and output. We can derive the track and draw the track of the HydroGNSS on a specific site. We have here the map of the site, and we can select from the user interface the value of biomass, moisture, roughness, or other parameters which characterize each of these land cover. Then we can provide error for what concern the system, for instance, error in attitude, error in power, in transmitted power, mismatch of the antenna, in order to finally produce the level 1A data for subsequent processing from the other level 1 and level 2 modules. So in conclusion, the end-to-end simulator can enable assessment of scientific readiness level 5 of the mission. It accounts for confounding quantities related to the observed scenario and the different geophysical parameter that also act as a nuisance parameter with respect to the one that is targeted by the application, and also the confounding quantity due to instrumental effect. The first order functionalities are almost all in place. As for the physical modeling of the wave interaction, electromagnetic interaction, we have a presentation tomorrow from Leila Guerriero at 9:40. And now what we are doing now before PDR is mainly working to enlarge the range of simulation that the simulator is able to afford. This is because simulating as we will see tomorrow, the simulation are quite heavy in terms of algorithm and in terms also of computational time. So we have to try to speed up the simulation as much as possible to be able to let's say, assess the performance on a range of variability of surface parameter and the instrument effect as large as possible. That's all from my side.
Thank you, Mauro. So far, there are no questions. So maybe I can ask you a quick question on the resolution of this the age savers part. So up to which detail do you need to characterize the surface? Can you provide inhomogeneities of the terrain and the cover at meter resolution, submeter, kilometer?
Okay, now from the work that we have done in previous experiments, comparing the outcome of the simulator with the data from Pdgs and from Cygnus, we have found that a good compromise is considering, because the topography is one of the main effects on the signal, we have found that the good compromise is considering a digital elevation model with a horizontal resolution in the order of 300 to 500 meters. So this is the resolution we are working now. Increasing the resolution is quite difficult in terms of let's say, computational time. As for specific application like the one that can be possible with the complex channel, you know, Estelle, that this is a second order functionality of the simulator, and in that case, for sure, we have to consider higher resolution, but for sure, we have to simplify a bit the type of simulation, because including also the topography, I guess that could be very heavy in terms of computational burden. But now the answer is about 500 meters.
Okay, thank you very much, Mauro. Now we've used up our spare time, so I think we're going to move on now. Thank you very much, Mauro. There will be another talk on a similar subject tomorrow. I have to make an apology on behalf of Klaus Scipal. He was going to be presenting on SMOS and biomass introduction and complementarity. And that's a very important connection that we could make with HydroGNSS. So we will make contact with Klaus Scipal at a later point. He sent his apologies. He's had personal reasons why he's had to drop out. So moving on to the next presenter then. It's Clara Chu, and I have to say, yeah, Clara Chu is a project scientist at the University Corporation for Atmospheric Research, and Clara was amongst the first people to actually identify just how good high-resolution GNSS-Reflectometry could be. We all assumed it was going to be around 25-kilometer resolution, but then she started finding the coherent reflections. But no doubt she'll tell us more. But we've quoted Clara quite a bit in our proposal documentation. So we'll hand over to Clara. Now, are you going to be giving a video, Clara, or are we playing it?
I was going to talk live, if that's okay.
Okay, no, that's fine. Please do.
If it works, we'll see.
Yes. All right. Well, over to you, Clara.
Okay. Let's see. Okay, can you guys see my screen and hear me?
Yes, we can.
Okay, great. That's a miracle. So thank you, Martin, and Estelle and everyone else for letting me give this talk today. I am super excited to see what HydroGNSS can do. I think it's going to be a really cool mission. Today, I'm going to be talking about soil moisture signatures that we've seen in the Cygnus data. But just for those of you who I don't know, just a quick walkthrough of my background. I've been looking at how GNSS reflections can help us sense soil moisture for the past 12 years now. During my PhD, I looked at how we can use GPS reflections recorded at geodetic GPS receivers to retrieve soil moisture. Then I did a postdoc at JPL where I was mostly looking at data from TDS1, also for soil moisture applications. And now that I'm at UCAR, I've been pretty exclusively focusing on Cygnus data and its relationship with soil moisture and other surface hydrologic parameters. And that's what I'll be focusing on today. So this talk is going to be split up into 3 broader sections. The first will be just a short introduction to soil moisture, why we care about it, how we usually measure it. I don't assume that most of you think about soil moisture every day, so I thought it would just be good to give some context as to what we already know and where we currently stand in our capabilities for measuring soil moisture. Then I'll talk about my own experience with GNSS-R, specifically in terms of Cygnus and soil moisture. And then I'll also try to summarize where some other research groups are in terms of deriving soil moisture retrieval algorithms using Cygnus. And then finally, I'm going to spend just a tiny amount of time talking about where I think we could go next with soil moisture remote sensing with GNSS-R. And hopefully at least some of this will be relevant to the HydroGNSS mission. Okay, so let's start with a short intro on soil moisture. And obviously the first question to ask ourselves is, what is soil moisture? And the answer is pretty simple. It's the amount of moisture or water that's contained within the soil, the dirt, the ground beneath your feet, whatever you want to call it. Soil moisture specifically refers to the amount of water that's in the vadose zone, which is the unsaturated layer of soil that lies directly beneath the surface. Soil moisture is highly variable through time, with space, and with depth. So if we were to look at a layer of soil head on, as I'm showing in the picture on the left, we would probably see the moisture content of the soil vary pretty significantly as we go down into the soil column. But in general, soil moisture has the most variability near the surface. And for this talk, when I refer to soil moisture, I'm really just talking about soil moisture in the top 5 centimeters of the soil column, because that's effectively the sensing depth of the L-band signals that GNSS-R uses. And then soil moisture at the surface can also be highly variable across the landscape. On the right, I'm showing an aerial view of an agricultural area and how soil moisture varies across the landscape there. And this just shows that there can be large changes in soil moisture that can happen even within the span of a few small kilometers. So why do we care about soil moisture? Soil moisture is interesting because it's one of the big factors determining whether the landscape is going to experience fires or floods. And it also plays a key role in the regulation of surface temperature. There are also known feedbacks between soil moisture and precipitation. So in some areas of the world and under certain conditions, after it rains, the evaporation of the soil moisture back into the atmosphere actually makes it more likely to rain again. So accurate knowledge of soil moisture is also important for weather forecasting. So soil moisture is important, but how do we usually measure it? I would classify our ability to measure soil moisture in kind of 2 broad categories, either in situ observations or point measurements. These could be gravimetric samples or observations from soil moisture probes. And then we also have satellite observations. Now, in situ or point measurements tend to only estimate soil moisture for a really small volume of soil. And because soil moisture varies so much across the landscape, you really need a lot of samples or observations in order to understand how soil moisture of the complete landscape evolves through time. And then kind of on the other end of the spectrum, we have satellite observations. Sorry, I don't know why that did that. We have satellite observations, and these tend to be larger aerial averages. And both NASA and ESA have already invested a lot of money into satellite observations of soil moisture, whether they be microwave radiometer missions like SMAP or SMOS, or active radar like the upcoming NISAR mission. Now note that all 3 of these missions that I mentioned here carry L-band microwave instruments in order to retrieve soil moisture. And that's because L-band signals have a relatively long wavelength in comparison to other microwave signals, which means that they can penetrate further down into the soil column, as well as penetrate further down into vegetation canopies, so that we can really sense what's going on at the surface. And I think that we are all well aware that GNSS-R data are also at L-band, which also makes them ideal for retrieving soil moisture. And this is where I'm going to start talking about my own experience using GNSS-R data from Cygnus to retrieve soil moisture. So in case you aren't already aware, Cygnus stands for Cyclone Global Navigation Satellite System, and it's a constellation of 8 GNSS-R satellites launched by NASA in late 2016. Cygnus was designed to retrieve ocean surface wind speed during hurricanes and tropical storms, and because of this, the 8 satellites chase each other around the tropics, collecting GPS reflected signals opportunistically. In the video I just showed you, these were Cygnus observations collected over one typical 24-hour period. Over time, the pseudo-random surface reflections tend to fill in to provide complete spatial maps of the reflected signal. So here I'm showing a long-term average map of reflectivity data over the land surface. Reflectivity is just one of many variables that can be derived from Cygnus data, but it's the one that I personally use the most often. And as we look at the land surface, we see areas of both high and low reflectivity. high reflectivity tend to concentrate in areas that are topographically flat, areas near waterways or known agricultural areas. And then low reflectivity tends to concentrate in either dry or topographically rough areas, though these two scenarios tend to go hand in hand with each other. Even before Cygnus was launched, we knew that, like all radar observations, Cygnus data over the land surface would be sensitive to both water in and on the land surface, as well as surface roughness. Hopefully change. Oh, there we go. So the first thing that I wanted to understand after Cygnus was launched was how the data changed when soil moisture changed in order to quantify its sensitivity to soil moisture without having to think about the surface roughness effects too much. And to do this, I looked at data over India. Northern India undergoes pretty large, spatially homogeneous increases in soil moisture throughout the summer monsoon season. And I thought that this would be one of the easiest places to see any potential sensitivities of the Cygnus data to changes in soil moisture. So I started making maps like these, where here I'm showing some selected monthly averages of reflectivity data from Cygnus over India. And then I compared them to coincident soil moisture retrievals from the SMAP satellite. And when I calculated the correlation between changes in soil moisture from SMAP and changes in reflectivity from Cygnus, it was super obvious that changes in reflectivity were pretty well correlated with changes in soil moisture. And this, of course, doesn't mean that there aren't other variables also affecting reflectivity, but it was pretty apparent that soil moisture is one of the most important ones. So I ended up writing a proposal to derive a soil moisture retrieval algorithm for Cygnus data beyond just showing these empirical sensitivities. But you know what happened? That proposal was pretty solidly rejected. But to tell the truth, I was pretty close to having finished kind of a prototype bare bones retrieval algorithm. So I decided to finish it anyway in the hopes that others who were developing perhaps more complicated soil moisture retrieval algorithms could look at my output to see where simple methods work, where they don't work, and hopefully improve upon them in the future. And I called my Cygnus soil moisture product the UCAR CU Cygnus soil moisture product because I worked with my former PhD advisor at CU, Dr. Eric Small, on it. And you could classify my retrieval algorithm as an empirical algorithm. I based it off of the sensitivity analyses that I had already done with the SMAP data. What I assumed was that for any given location, you could approximate the relationship between SMAP soil moisture and Cygnus reflectivity as linear with a slope equal to beta. And that's what I'm showing in the conceptual scatter plot at the bottom of the slide. I allowed beta, or the slope, to vary across the surface, and that's what I'm showing in the global map at the bottom of the slide. And I allowed the slope to vary across the surface because I thought that depending on the overlying vegetation, it was reasonable to assume that the sensitivity parameter beta could change depending on the vegetation cover. And for this bare bones algorithm, although I allowed the sensitivity could change through space, I didn't allow it to change through time. But you could imagine that as vegetation grows and then senesces throughout a season, that the sensitivity of reflectivity to soil moisture could also change within the season, but currently my algorithm doesn't allow for that. When I validated the product against in situ observations from soil moisture probes, and at the top of the slide, I'm showing just one example, I found that it had comparable uncertainties to SMAP, which made sense because I had effectively calibrated my reflectivity observations to SMAP. One quote unquote advantage of the Cygnus soil moisture product relative to the SMAP product was that because of the way I averaged the data, you actually get soil moisture data more often for any one location with the Cygnus product than you do with the SMAP product. And this in theory would allow you to investigate shorter term variations in soil moisture than you currently could with SMAP. So I put this product out on the internet through our public data portal, and at this point, that was almost 3 years ago. And since that time, there have been several other research groups that have started developing their own soil moisture retrieval algorithms using Cygnus. Some of these algorithms are empirical, like mine, which regress reflectivity or other Cygnus variables against various ancillary truth soil moisture data sets. Other other algorithms are semi-empirical, where maybe they've derived a theoretical relationship between Cygnus and soil moisture or vegetation parameters, but then they still have to rely on ancillary data sets to then parameterize their models. And then there are also several machine learning algorithms that have started to be published. So far, it seems like all of these algorithms have shown at least a moderate amount of success at using Cygnus to retrieve soil moisture. It seems like no matter what algorithm you try, you're going to probably get at least reasonable results. We are just now starting kind of a algorithm intercomparison effort where we're going to see which algorithms perform better under which conditions and where, but that effort has just started like a month ago. So we can't really say which one of these algorithms is the best under what conditions. But I think that one kind of complicating thing about this intercomparison effort, but also one cool thing about the products, is that almost all of them are gridded to different spatial and temporal resolutions. And I think that this opens up the opportunity to answer several different types of science questions than you could answer if you were only provided with one data product at one spatial and one temporal resolution. And I think this point leads me to here, which is talking about where we might be able to go next, or maybe more appropriately, ways of thinking that I personally want to work towards. I think that a lot of us working with Cygnus data, and I include myself in this list, we've kind of fallen into a trap of trying to make Cygnus data look like data from other remote sensing instruments. And we get really frustrated that Cygnus data, they aren't collected in swaths and they aren't collected at consistent local times. And this is seen as a really limiting characteristic of the GNSS-R data. And I think we spent a fair amount of mental energy trying to mitigate these aspects of the data. It's also caused a lot of debate in terms of the best way to kind of shove our data onto a typical rectangular grid and what size those rectangular boxes should be. But I think that's, although this is important, it's important to investigate this, it's important to do, I think it's maybe also missing a larger point where there are a lot of science questions that might be better answered by not pretending that the environment is made up of arbitrary boxes. And I think that HydroGNSS in particular has the unique opportunity of exploring maybe some of the off-the-wall ideas of how we interpret our data and what sorts of questions that we can answer with it. So that's just something that I've started thinking about. I don't have any answers or good ideas, but I think that GNSS-R data have the potential to provide new and different information, and maybe they don't always need to be forced to fit into the traditional remote sensing paradigm. And with that, I am going to finally stop talking, and I'd be happy to chat if you have any further questions. Thank you again for the opportunity.
Thank you, Clara. As always, a very interesting talk and posing questions. This is also a classic from you. I don't see any questions yet, but maybe I'm not sure I understood your last sentence. Could you explain a bit better?
Oh, well, we have this cool track data and it's randomly collected over the surface. And I think that we get frustrated that we can't make these regular gridded maps every day. And I think in particular, when we talk about the temporal resolution of our data, you might say, well, if we make 3-kilometer maps, we only get them once a month. And then that's seen as kind of a ding on the data compared to other remote sensing instruments. And I just think maybe if we kind of emphasized the gridding a little less and thought about what science questions we could answer with the data as they are now, maybe that would be one new avenue to kind of explore. And maybe it would go nowhere, but that's just something I've been thinking about as I've been working from home for the past 2 years by myself.
And thank you, Clara. And follow-on question to that, and is one of the things we're struggling with is that sometimes when you've got diffuse surface, you get coarser resolution, and then you get flatter surface and you get finer resolution, and you get less coverage with the finer resolution. So I don't know if you had any quick thoughts about that.
I mean, so one thing that I would like to look at, which I know that I just talked about, let's not grid the measurements, but kind of doing an adaptive grid style like they do with groundwater modeling or other, I think they maybe do it with atmospheric modeling too, where you have this adaptive mesh where you can have a variable grid sizes across the surface. I think one thing you'd want to think about is, you know, let's say you have this rough surface that normally has this really coarse resolution and then it floods. Now all of a sudden your resolution shrinks, and how you deal with that. I think that's still an open question that nobody's really been able to solve yet.
And hopefully with HydroGNSS, we're working towards two measurements. You've got the one coarse measurement, the incoherent EDM, but then you also have the coherent channel as well. So we have two measurements of the same surface, and maybe that will tell us something new.
Yeah, I bet it will.
Yeah, this is aligned with what Jean-Air commented 2 talks ago about using level 2 products, along track products rather than gridded products. And that's the type of observables preferred in numerical weather prediction. So maybe one of the things we should look at in the future is to assimilate data in models, not only numerical weather prediction models, but also hydrological models and other types of models. And then maybe this arbitrary or random-like distribution of our observations is less critical.
Yeah, and I think they're both super, you know, like gridded products have their place and track products have their place. And I think with Cygnus, we kind of focused a lot of our energy on the gridded products just because we have so many observations. But I think, you know, you guys might be able to really discover some new things by looking at the track products as well.
All right. Well, thank you very much, Clara. We've got a lot of talks tomorrow. Thank you for making, Clara couldn't make it the next day, so we invited her to present this afternoon. But I think that pretty much wraps it up for today. So it's been an exciting day, lots of very good talks and exciting themes. And we've got a lot to look forward to tomorrow. It's a bit less about TDS itself, it's more about related research and potential users and parallel missions, and whether there's more we could learn from missions such as Cygnus and others. And then we're going to end tomorrow afternoon with the roundtable to put together some of the thoughts and some of the questions and where we go next. But so I think that pretty much ends today. I'll hand back over to Ben to maybe say a couple of final words.
Yes, thanks, Martin. Well, you've pretty much said it there, really. I think, you know, it's been a great day. Thanks to all of the speakers for their insights, and thanks to all of the attendees for your attention. As Martin said, tomorrow we'll return to hear from scientific users of the mission, synergy with other missions, and we will have a session on future opportunities for collaboration along with a roundtable.